Hi, everyone. Thank you all for joining us here with the School of Physical Sciences Compelling Conversations. We're just kind of getting set up here, so I have this slide ready to sort of prepare everyone for what we're going to talk about today. Before I introduce our guests, I just want to say a few very preliminary things, and then I'll stop screen sharing and commence in earnest. So, as advertised, this discussion is titled "What is Known and Unknown About Climate Change?" And as I'll mention in a little bit, one of the things we really welcome here is support for the kind of research that you're talking about, that we will be talking about. If you want to support this research, it's easy to do. You can text to give. And so what you do is you get out your cell phone and to the number 41444, you text PSCC, and you'll be sent a link, and it should be straightforward to do. And just so you know, even rather modest amounts of money can be incredibly useful at this time. Even $10 can have an impact. And one of the reasons is that, the research that we're doing, a lot of this is supported by federal grants, but you typically have to use these federal grants to support research that you've already described and proposed to do. But if you have a brand new idea that's urgent that you want to work on and sort of do some seed exploration, a lot of times the cycle to get funded on a federal grant can be longer than a year or sometimes even up to 2 years. And so there's this delay. So donations of this kind can really enable research programs to be jump-started and then eventually be picked up by longer-term funding opportunities. So appreciate everyone thinking about that. So let me go ahead and stop my screen sharing so you don't have to look at that slide anymore. This is our group. Let me welcome all of our guests and our panelists. My name is James Bullock. I'm the Dean of the School of Physical Sciences here at UCI. First, I'd like to thank all of you who participated in our survey. Your feedback is really appreciated, and we heard you, and we're planning on programming around areas of interest that you highlighted. And in fact, today's discussion of climate change was the #1 requested topic, and that's why we scheduled this event today. So what is this series? So this is Compelling Conversations, which is an exclusive virtual opportunity for partners, alumni, and supporters of the school. Each event will be a live, unscripted conversation among world experts on imperative topics. This ongoing series is going to be offered at roughly a monthly basis. As I've said before, please consider supporting the groundbreaking research of the kind we'll discuss today. And you can do so by texting to 41444, the letters PSCC. Now, if you have any questions you'd like to direct the panelists, please utilize the Q&A button at any time during the conversation. My role in this, I am not a scientist who works on climate change as my expertise, but what I'm going to be is sort of the moderator. I'll look at these questions, I'll monitor the questions, and then direct them to the panelists when the time comes. So finally, let me introduce our panelists quickly. So first we have Kathleen Johnson. Kathleen Johnson is an associate professor of Earth System Science. She's also the vice chair for diversity, equity, and inclusion. Professor Johnson's research focuses on developing high-resolution records of past climate called paleoclimate. And she's using, for example, cave site formations and other archives from China, Laos, California, and other regions. She's an expert on caves, climate change, and past climate variability and geochemistry. She holds a B. Jim Randerson. Professor Anderson is a Ralph and Carol Cicerone Chair and Chancellor's Professor at the Department of Earth System Science. He has a BS in chemistry from Stanford, a PhD in biological sciences from Stanford. He's also an elected member of the National Academy of Science. Professor Randerson's area of research includes climate carbon cycle feedback, fires, land coverage change, remote sensing, tropical deforestation, global change in the Arctic, terrestrial ecosystems, and climate policy. Finally, we have Professor Eric Regneau. Eric is the chair of the Department of Earth System Science. He's Donald Bren and Chancellor's Professor as well. He's also a senior research scientist at NASA's Jet Propulsion Lab, Radar Science and Engineering. He holds degrees in an undergraduate degree in engineering, master's degrees in astronomy and astrophysics, and in aerospace and electrical engineering. He also has a PhD in electrical engineering. He is also an elected member of the National Academy of Science. He works to understand the interactions of ice and climate, in particular, how to determine how ice sheets in Antarctica and Greenland will respond to climate change in the coming century and how they will affect global sea level rise. So as you can see from this introduction, the breadth of expertise in the Department of Earth System Science alone is represented by the folks on this call. And it's exactly the viewpoint that we have in this school and in this department, that bringing in all of these diverse areas of expertise to think about the Earth as a system is going to be really crucial for us to understand and tackle climate change. So with that, I'll try to talk less from now on. I want to start by asking Kathleen, tell us a little bit about how you got to where you are now doing your research and where you see things now with climate change.
Sure. Yeah. First of all, thanks a lot for having me. I'm really excited to have this conversation with you and Eric and Jim. So I have a background that's a little bit different from a lot of the faculty in the department. And that's, of course, one of the strengths of ESS is that we have faculty that come from these wide range of different fields, all to study the Earth system. So I believe Dean Bullock's video froze a little bit, so you might have missed that I have a BS and a PhD in geology. So I really come at this with this long time scale, deep time perspective about the Earth system. And so as a geologist, you know, we tend to think about how we can use the past history of our planet as a guide to the future. So that's something we often hear. And with paleoclimate, or the study of past climate change, I initially didn't know anything about it when I was an undergraduate, really, until I took a couple of classes on geochemistry and sedimentary geology. And I became fascinated with this way that we can actually unravel this giant mystery of how Earth's climate has evolved, how the Earth system has evolved over these long time scales by using natural, physical or chemical or biological records preserved in rocks. And of course, paleoclimatologists also use fossils, they use organic molecules in sedimentary records. And we use all of these things, which we refer to as proxies, because we don't have a time machine. We can't go back and look at what climate was like, you know, 10 million years ago or 100,000 years ago. We need to rely on these indicators, these proxy indicators, which are sensitive to the climate, the time that they were deposited or formed. And so I really love that aspect of discovery, where we can really learn more and more. The deeper we dig into paleoclimate, the more that we learn and the more nuanced information we can get. And I think, personally, I think that paleoclimate is still extremely important as we are moving forward and trying to understand how climate changes will unfold in the coming decades and centuries. And that's because they're the only source of information we have about different climate states than the present. So most climate models, and Jim, I'm sure, can talk about this much more in detail, but most climate models that we have are tuned to be able to simulate current climate or pre-industrial, climate over the last century or so. And they do that quite well. However, we know from the geologic record and from the paleoclimate record that Earth's climate has varied over these wide range of timescales on a number, everything from sort of a million-year plate tectonic kind of timescales all the way to sort of interannual timescales related to things like El Nino. And given that the instrumental record of climate is so short, we're only capturing a small range of natural climate states. And so paleoclimate provides the only opportunity we have to provide evidence for what the climate looked like, how quickly it changed, what the scale of those changes were, on these longer time scales. And so even though no perfect analog exists in the past for what we might expect in the future, we do have these different climate states that we can use as a test to see what Earth looks like under different levels of CO2. We can look at how ice sheets and sea level responded. We can look at how global temperatures responded. So what is the sensitivity of Earth's temperature to CO2? We can look at how hydroclimate changed. So how regional rainfall patterns were affected under different climate regimes. And we can also look at some of these like transient events, like really abrupt climate changes that occurred and how the Earth system responded to those. And so I guess based on all of that, paleoclimate provides the strongest evidence that what we're doing today to the planet is really unprecedented. The rate and the magnitude of changes that are happening are much faster and larger than anything that we know from the paleoclimate record. So I guess that's what I'm excited about, and that's why I think paleoclimate's important. My own research in particular focuses on studying past changes in the water cycle, primarily in the tropics. So especially in the Asian monsoon region, we're using these cave deposits, as Dean Bullock said, to study past changes in rainfall. We can also learn information about past changes in vegetation from these events. And we use these to study the Asian monsoon system, climate in northern Mexico, and other regions where current climate models don't necessarily agree on how regional hydroclimate, or when I say hydroclimate, I just mean water related climate. So how regional precipitation patterns are going to change in the future.
Great. Kathleen, thank you so much. And we'll return. I think we'll have lots of questions related to that. I've already got one for you that I'm going to come back to in a second. Before we do that, I'd like to ask Jim to give us a brief introduction to how he got here and what he's most interested in working on these days.
Sure. Yeah. I got interested in global change and the environment. I think I took a class as an undergraduate in photosynthesis, and I was excited about that. That was on like DNA repair and very fine scale mechanisms controlling that. And one of my teachers told me about a group that was thinking about how global environmental change and humans, how they were changing ecosystems. So I started working on a group, and for my graduate work, I actually looked at the breathing of the biosphere. I was looking at the imprint of how every year there's an annual cycle of carbon dioxide in the air, and this annual cycle is now rising from the impact of all our fossil fuel burning. But embedded in this signal of this annual cycle is a lot of information about how the biosphere, the forests of the world and the oceans are changing CO2 and how they're responding to all these changes that we're imposing from climate and from changing atmospheric composition. So I was fortunate in grad school to work with a group that was building some of the first biosphere models. So it's like trying to estimate planetary photosynthesis. So I remember at one point giving a talk just when I started grad school about trying to estimate the level of photosynthesis for the whole world. And it was in the department, many people were focused on just the mechanisms of photosynthesis. And it was a really fun time to think about scaling, about what the world was able, how we were able to understand how the world is breathing. And we were really lucky at that time to take advantage of some new satellite data that was coming back from Earth observing systems. So, and then I, moving to UC Irvine, I really have focused on wildfires as one of the themes of my research lab. And I study wildfires. I've done field research in Siberia and Alaska and some in California. And I use a lot of remote sensing data from satellites that NASA has to study how fires are changing, how fires are responding to climate, working with some Earth system science undergraduates right now on a project to look at the 2020 fires and their sensitivity to these extremes and heat waves that we've been experiencing more frequently. And then one final thing that I would mention is that I'm thinking a lot these days about how we can improve our ability to detect fires more rapidly and study their spread. And so I'm involved with a group. We're putting together a proposal to NASA to build a new constellation of fire satellites, and it's with a company here in Irvine that makes CubeSats. And so we would launch a constellation of 10 little satellites that would measure fires at different times of the day and try to give us better early warning information about when fires are, when they start, and then how fast they're spreading over the landscape. And this has been a really a fun effort to be involved with to try to propose a new satellite system. So that's kind of a summary of where it come from.
Yeah, Jim, thanks so much for that summary. So many interesting things there that we'll definitely want to circle back on. Eric, let's make sure we get to you as an introduction here first. Please do give us a brief intro, and then maybe tell us a little bit about where you see the climate today, and you know, where do you think we stand in terms of climate change?
Oh, okay, thank you, James. Thanks for having me at this in this conversation. So I came a little bit from the side. So I have a background in engineering. I was always interested in math and physics as a youngster. And I came to science through the back door in a way, interested more in technology of remote sensing. I came to the NASA Jet Propulsion Laboratory and worked on satellite radar images and quickly fell upon some sort of exciting area of research. I was sort of at the right place at the right time, doing the right thing. And that followed through my whole career. I was always interested in polar regions, but not necessarily as a line of work. And with these satellite images, the field of studies of polar regions was transformed completely, starting in the 1990s. To put things in perspective, I had the chance to work with glaciologists who were the early explorers of the Antarctic continent, who got the first data there at the risk of their lives. And they would admittedly go to some places not knowing where the glaciers were. And we transitioned to a time where not only we know where the glaciers are, we can measure their speed almost continuously now and look at very interesting changes that early explorers could not even phantom because they did not have the possibility to give these measurements. So my transition to science was like opening a case of gold, a golden opportunity to explore new territory with this technology. And the irony of all of this is that this work also started to ramp up when we could pick up the science of climate change in the polar regions more and more. And the signal has only grown bigger with time, that to the point where we can't quite miss it anymore. But in the early 90s, this was still a time where part of the scientific community was a little bit divided on how much of climate change signal we're going to see in the climate system. And we're starting seeing some of this signal in the polar regions with these instruments. That was very exciting, a lot of exploration. And for a scientist, this is kind of a dream position to study a system that's changing so rapidly, because you get to understand a lot of processes, because you see these processes acting on the system in real time. So that's a little bit of an introduction. And coming to UCI for me was also transforming of my research. At JPL, I was more focused on mission, on processing, on driving the science, but in a narrow way. And coming to UCI and seeing what my fellow colleagues were doing in the Department of System Science, really sort of broadened my view of what I was doing and really helped my research in many different ways. In particular, I spend most of my time right now peering down at the depth of the ocean to study what's happening on the ice sheets. And maybe it's not something I would have looked at as quickly if I had not come to UCI and work in the Department of System Science.
Eric, thanks so much. Let me also say, I apologize. I'm having some issues with my internet. So if I glitch and come out, these three can keep going without me because they don't really need me at all anyway. Let me address a couple of questions and ask Kathleen a question of my own that's kind of moved into this. So To first order, how long has it been in the geological record since the atmosphere has had this much CO2? And you know, and more generally, you know, can you give us a Reader's Digest example of how one uses the geological, like, how one uses the record to figure out what past climate was?
Sure. Yeah. So yeah, one of the interesting things about paleoclimate is we can do a couple of different things. We can find proxies that are sensitive to climate conditions, whether that's temperature or rainfall or something else. But we can also actually provide constraints on some of the climate forcings, like CO2 especially. So carbon dioxide, of course, is one of the main forcings that affects our climate. And some of the best evidence for CO2 variations in the past, or the best evidence for CO2 variations in the past, comes from ice cores. But the ice core record from Antarctica only extends to 800,000 years ago. And so like what we know from that, which I think is something I always tell students, is that over this 800,000 years, there were these really regular cycles that were spaced out about 100,000 years. So there's 8 cycles covered from the Antarctic ice core record right now, where Earth fluctuated between these glacial states and these interglacial periods like we're in today. And the difference in atmospheric CO2 between those glacial periods and interglacial periods was about 100 ppm. So glacials, they were 180 ppm. Interglacials, they were around 280 ppm. And that's the same as pre-industrial CO2. And so that 100 ppm difference is the difference between having kilometers of ice over New York City versus having the climate we have today. So for context, today we are 130 ppm higher than the pre-industrial CO2. So that is a much bigger difference than you have between these two very different climate states. So that's like something that I think helps provide some perspective. If we want to go back further in time and ask when was CO2 as high as today, there's unfortunately no ice core records that go back that deep. But there's other proxies like geochemical proxies that we can use to infer past CO2. And I don't do this work myself, but they include things like carbon and boron isotopes are 2 of the best proxies that can be used. So boron isotopes are actually used as a tool for reconstructing the pH of the ocean. So they measure the boron isotope composition of these shells. So the ratio of boron 11 to boron 10 in these carbonate shells of plankton. And then that actually is known to relate very closely to the pH of the ocean, which you can then back out the CO2. And similarly, carbon isotopes are used in that way. And there's other different types of proxies as well. So things like the density of stomata on leaves, on fossil leaves, has been used to reconstruct CO2. And all of these methods, of course, have some uncertainty associated with them. So it helps to try all of them and have lots of data overlapping, and so that you can hopefully converge on an answer. And right now it looks like the last time CO2 was as high as it is today was probably in the mid-Pliocene, so around 3 million years ago. But that was perhaps only a transient period. And the last time CO2 was as high as this for a sustained period may have been as long ago as 30 million years ago or 50 million years ago in the Eocene. And there's very good evidence that, you know, if we continue on this business as usual trajectory, we are going to reach CO2 levels that haven't been seen in 50 or even 100 million years. So we have had CO2 concentrations as high in the past due to natural processes, but it's been a long time, and the world was a very, very different place at that time as a result.
Wow, so you're saying that the last time the CO2 levels
I can try. Sorry, you froze there for a second. I was going to try and guess what you were going to ask, but you can try again.
I'll try one more time quickly. So you're saying the last time it was this high, there not only were there no Homo sapiens, there were dinosaurs. Like, it's been a long time, right?
Yeah, pretty much. So it's really, and those changes were driven by volcanic activity and the balance between volcanic CO2 release and chemical weathering of rocks, which basically removes CO2. And so those changes happened over a very, very, very long time period, whereas we might do the reverse. So I'm talking like 100 million years of change in CO2, and we could potentially do the reverse in something like 10,000 years.
Wow.
Or less.
Yeah. Fascinating. So we've got another question here from John Evans. And this probably goes to Jim, at least we'll start there. How are recent fires impacting the atmosphere, and how about deforestation? And are there efforts to replace forestation, and how does that factor in?
Yeah, just to add briefly before I start to Kathleen's line, yeah, so the CO2 is really high then, and it really connects Kathleen with Eric too, that there was no ice, I think, when the CO2 was that high, or there's very little ice, at least in Greenland, and maybe a little bit in Antarctica. So, you know, the world we're headed for is one that if you let it stay at an equilibrium for a long enough time, and it is true that all the gases we're putting in, it's somewhat irreversible. At least it'll take millennia for us to remove that carbon dioxide slowly out of the air, unless we use some other technique, that some kind of geoengineering. But we're setting the Earth on a path that where there was not as much ice as there was once. And yeah, on the fires, yeah, I studied this. I'm working on a paper right now on some of the deforestation, and the deforestation is contributing to the buildup of greenhouse gases. It's about a tenth. Most of the greenhouse gas buildup is from our burning of fossil fuels. And about a tenth of that is coming from deforestation. And the deforestation emissions can be tracked using satellite observations, both of forest cover from these satellites. There's a great set from the US called Landsat, and the European Union now has one called Sentinel-2, that's got a great way of measuring deforestation. You can also see fires as well there. And so in my work, we've actually been tracking the fires. This is with also a new assistant professor in earth system science, Paulo Brando. We're trying to track the fires in the Amazon in near real time using satellite measurements of thermal anomalies. And we're actually measuring, often deforestation, they'll use fire to combust the material. And sometimes these fires will escape from a place where the field is being cleared, and they'll burn into the understory forests around it. And so we're actually trying to track these understory fires as they grow and provide this information to firefighters in Brazil and in Peru to try to target fires during really during the dry season. We had a pretty intense dry season in 2019, and there was also a lot of burning in Brazil, also in the Pantanal region just to the south in 2020. So it's really a threat, the deforestation fires, and they're a threat both for the buildup of greenhouse gases, but also just a threat to the actual the functioning of the Amazon, which is really part of the lungs of the biosphere. And we don't want to incite like a positive feedback where we lose those forests, because then it will really change the regional climate and release a lot of carbon dioxide.
Thanks, Jim. We've got a couple questions here that are very specific, and I think it's important it would be useful to hear the answers from each of you, but I think I know what it's going to be. So let me ask the first one here. What percentage of the CO2 increase level do you attribute to humans versus natural causes in the last century? Who wants to take that?
I mean, I would say pretty much 100%, but Jim might.
That's right. Yeah. That's true. Yeah, absolutely. Right. We know from what Kathleen studies these isotopes that there is this big natural cycle of the breathing in the biosphere. And I think that's the second question too there, James, from Milanid, that there's a natural cycle, and the biosphere is breathing in a huge flux is going in every year into the plants and coming back out. But that systems have been at steady state with the ocean. It's reached kind of a stasis, or it's an equilibrium, and then this extra gas we're putting in from burning of fossil fuels and the deforestation has contributed to almost all the rise in carbon dioxide. And we know that because we can see the isotopic composition, the different, slightly different atomic molecular structure of the carbon dioxide. There's an extra neutron in some of the carbon molecules and on the carbon atoms, and we can see that it's got the exact signature of fossil fuels. And so that is actually a part of the story that we know precisely, incontrovertibly, that all the buildup of the greenhouse gas CO2 is coming from anthropogenic activity, mostly fossil burning, but also a little bit from deforestation.
Yeah, and another thing that a lot of folks in our department do is using radiocarbon measurements as well of the atmosphere or of annual grasses. For example, there's a current citizen science project where they're seeking annual grasses from across California to look at the grew this year to look at the impacts of COVID on fossil fuel carbon release in California. But that's something else that Jim and Claudia Simchik and some others in our department have been working on quite a bit, given that we have this amazing radiocarbon facility.
Yeah, well, thanks, Kathleen. Before I turn to Eric, I want to just chime in something with my physics professor hat on. You know, the way that we think about this is that, you know, for a long time, ever since there have been basically plants doing photosynthesis on Earth, they've been collecting all this solar energy and more or less storing it in the form of these carbon bonds. And that's been buried and buried and buried for 100 million years or more. And now we're burning it really quickly and releasing that carbon dioxide that took a really long time to absorb is now being released like that. That is not normal. And that's why things are so different now than they were in the past. And as an astronomer, anything that's happening on a time scale that's smaller than even 10 million years is incredibly fast. And so we're talking about a century now. So this is just unprecedented. I want to now turn to Eric because, you know, you're witnessing some pretty remarkable things firsthand when you're studying these glaciers. And I wonder if you could fill us in a little bit on what you're finding that's been surprising. You know, we have these climate models that have been sort of estimating how bad it, you know, what's going to happen with, say, ice sheet melt as the temperatures begin to rise. But you've discovered some things that are even happening faster than even some of the worst case scenarios we're suggesting, if I'm right. Tell us a little bit about that, what that was like to see it, and then how that, you know, what's your reaction to that in the context of this climate change crisis we're facing?
Yeah, you're right, Jim. Lots of amazing changes. To bring things in context with what Kathleen was talking about, we know from the paleoclimate record that sea level was rising much faster in previous times than it is today, even though today most of the sea level rise is from thermal expansion of the ocean and the melting of land ice. We're raising sea level by 3 millimeters per year, but there are time periods in the past where the rate was 10 times bigger, right? And that's sort of thing that keeps glaciologists up at night to figure out how could the ice melt so quickly at the poles during these past times, because we know it happened, and there's a good chance it could happen in this coming century or the next century. The physical processes have not changed. They're the same that operating in the past that are operating today. And it's telling us that when the ice sheets in the polar regions melt away, they don't melt just from the surface, from more radiation and an albedo feedback that melts the ice at the surface faster. The glaciers start to flow faster and disintegrate faster. And that eventually becomes the dominant factor in sea level rise. And what we're seeing today is just like the little tip of the iceberg, so to speak, of what's going to happen in the future, where we could have a rate of sea level rise that goes 10 times faster. So 10 times faster means we have 10 times less time to adapt to that. Also means that it's going to take longer for us to eventually stop the process or slow it down or eventually reverse it. So it's like launching a machine that in an irreversible path. So we've not seen the 4 centimeter per year yet, and this is a limit of what we don't know. We're trying to figure out how we could push the system that high to get these 4 centimeters per year sea level rise, because no human being has witnessed something like that. There were no humans when this happened on the planet, measuring the effect of sea level rise or land ice melting at the poles. Now, to put things in context, no one expected to see such drastic changes in the polar regions. Probably most of us are familiar with the retreat of mountain glaciers. You can go to the glacier national parks in the US and see the retreat of glaciers. You can see on the pathways where the glaciers were at the beginning of the 20th century and where they are now. You're going to walk a few kilometers and see the remainder of the glaciers. But what's happening today in Greenland and Antarctica is another scale. We might think that the changes occurring in Greenland and Antarctica are much less than what we're experiencing here in our warm environment. But what we're finding out, it's the opposite. Glaciers in Greenland are retreating about 0.5 kilometer per year, and glaciers in the Antarctic are retreating in some places 2 to 3 kilometers per year. Right? So if you could build a trail on some of these Antarctic glaciers, you could build a trail that goes back 30 years now, and you say, okay, 30 years ago, this glacier was right here, and now you're going to have to walk 100 kilometers to find it again. Some of the changes we're seeing in the polar regions are most pronounced in the places that are sort of the coldest, because they're suddenly affected by a new climate system that profoundly changes their environment. One of the probably most important thing that we found out studying these areas is that yes, there's the melting from the surface, but there are vectors of rapid changes coming from the ocean. It's not just the ocean warming up, it's also the atmosphere circulation changing and pushing the ocean currents differently and bringing more warm water in contact with the ice. And the ice reacts to warm water from the ocean just like that, incredibly fast, and provoking some very drastic changes in the Antarctic and Greenland. So that's the focus of the research right now. And it's also something very challenging to put in models, because you really need to have the state-of-the-art climate models to reproduce these subtle changes in ocean circulation along the edges of the ice sheets.
Thanks, Eric. I'm going to ask a couple of the questions that have popped up both in the chat and in the Q&A. So the first one is, I think I can answer quickly. Tell us again, what is the past natural cycle for the CO2 fluctuations? I think that's with glaciations. About every 100,000 years, you see a cycle. And so what we're seeing is a 100-year timescale rise on top of a 100,000-year natural cycle. And so that's why it's so glaring that this doesn't look natural. Another question has to do with, and maybe I could direct that to Kathleen. You talked about how a very long time ago, the CO2 levels were approaching as high as they are now. What is this natural CO2 cycle? How did the Earth recover? What is that cycle over which the CO2 goes up and down? And maybe that would be an idea to sort of briefly explain why it takes so long for the Earth to sort of react.
Sorry about that. So yeah, what we're talking about is sort of the geologic carbon cycle, basically. So we think a lot about the carbon cycle today being driven by changes in ocean uptake, fossil fuel burning, the biosphere, et cetera. But on long timescales, like these millions of years timescales over Earth history, CO2 has varied dramatically, as high as maybe 7 or 10,000 ppm, for example, during the Cretaceous period. And that has been driven primarily by changes in these two geologic processes, volcanic CO2 degassing. So the rate of volcanic CO2 emissions on average is very low. It's something like 0.1 or 0.2 petagrams of carbon per year, compared with like fossil fuel emissions, which I think is like maybe 50 times that or something like that. And so that really slow rate of release means that it can take, if you have a sustained period of volcanic activity that's driven by some change in plate tectonic processes, then that can add CO2 to the atmosphere and create these really high CO2 concentrations. So some of those like earlier high CO2 worlds are thought to have been driven by these periods in the geologic past when you had massive amounts of volcanic activity, submarine volcanic plateaus, and flood basalt deposits, which are huge, massive volcanic episodes that were much bigger than anything that has been seen in recent millennia. And the opposite mechanism, the sink for carbon on those timescales, the dominant one is chemical weathering of silicate minerals. And so essentially CO2 in the atmosphere reacts with water in precipitation, which forms a weak carbonic acid, which then chemically reacts with silicate minerals, which are the most abundant mineral type on the land surface, and then forms a series of dissolved ions, including dissolved inorganic carbon, which then gets transported to the ocean, taken up by either photosynthetic organisms or incorporated into shells, calcium carbonate shells in the ocean, sink to the bottom of the ocean, get buried in sediments, and then eventually stay there for a very long time. So basically, it's those two processes and the balance between those two processes, which is thought to drive. So in terms of how Earth's CO2 decreased over time, it was thought to be driven by increases in the chemical weathering rates. There's other examples too, like for example, the uplift of the Himalaya mountains has long been thought to, that was these continental collisions where you have two tectonic plates that collide together, form these massive, massive mountain ranges. These are actually relatively rare in Earth history. And when you do that, you expose a huge amount of fresh mineral surface, basically. And so that could increase the chemical weathering rate and increase that drawdown of CO2. So much of the drawdown and decrease in CO2 over the last 50 million years has been one of the dominant hypotheses to explain that is that it's this increased chemical weathering in part driven by this availability of all this fresh material to chemically weather. So it's generally like plate tectonic processes, volcanic activity, and weathering, some sort of balance between those. And there's still an awful lot of debate and active research about the details of all that.
Thanks, Kathleen. Let me turn to Jim now for another question here, which I think is quite interesting. Is it possible to plant enough plants to significantly offset fossil fuel production? That is, can we plant enough plants to suck in enough CO2 to offset what we're doing?
Yeah, that's a good question. There's been several lines of research that recently were published, one in Science, and I was involved in a paper that also kind of responded to that initial paper that suggested there was a lot of potential for slowing the buildup of CO2 by growing more forests. And there is some potential, I think. California has an offset program for trading carbon credits, and many of the projects involve enhancing forestry. We're doing research as a part of a California Ecosystems Climate Solutions project that's led by a colleague, Mike Goulden, to explore the efficiency of these carbon offset projects. And we're very much in the very preliminary stages, but they're effective, I think, but not as effective perhaps as they're being credited for. And there's a lot of risk too. When you grow more forests in some places in California, we know from climate change that the risk for fires is increasing, especially in lower elevation forests in central and northern California. And so placing all your eggs in that basket, knowing that the fire season is getting more intense, it's getting hotter and drier during summer, is one that may lead to a situation where some of that carbon that's being stored is impermanent and is released back to the atmosphere. So I think there's some potential, but the main solution has to focus on reducing fossil fuels. In many places where you grow forests, I've done work on this in Alaska and in California, if you grow a forest above a desert or above a place where there's a lot of snow, you might actually bring in carbon dioxide, but you may actually heat up the planet because the dark forests tend to be darker. And if you're covering up snow, you may be delivering more energy and heat to the lower atmosphere And that's problematic because the winds might take that heat across to Greenland, where Eric studies. And then you might actually accelerate a little bit the melting of the ice. So forests, we should invest in forests in trying to especially slow deforestation in the tropics. That's critical. There are many co-benefits of that. There's many benefits to slowing the rate of drought-induced mortality in California. But again, like the main driver of humans is our consumption of fossil fuels. So I would just highlight that it's so critically important. This is what Stephen Davis in our department studies, trying to decarbonize our economy, switching over to wind, switching over to solar, and getting us off of fossil fuels. Keeping the fossil fuels in the ground is the best way to slow climate warming. And it's one that I think forests can have a role, but it's got to focus mostly on this decarbonizing our electricity and our transportation.
So before I turn to Eric, I want to bring his thoughts in on another question we have about science communication and policy. I did want to sort of echo some of what Jim said and take my chance to brag about the school. It's one of the things we're very proud of here at the School of Physical Sciences. We have people in the chemistry department and the physics department collaborating with folks in engineering to really work on climate solutions. And we are about to launch within the UCI community a new effort called Solutions That Scale, which is focused on this, that will involve all the folks you see here and then others on campus. One of the things you will learn if you talk to a chemist who's working on carbon capture, they'll say entropy alone says it's going to be much easier not to burn it than it will be to suck the carbon back out of the atmosphere. You'd rather not spill the milk than clean up the milk. Cleaning up the milk is always harder than spilling the milk. And coming up with new ideas about energy storage with hydrogen, or maybe even energy creation with clean fusion energy, as some of our physicists are exploring, might be ways forward in those directions. But let me, we've got a couple questions that are starting to turn a little bit more towards policy or scientific technical solutions. But I'd like to get Eric's perspective here. I mean, we have a very specific question here, Eric, which is, what avenues do you take to communicate your science to the non-scientific community so that policies and decisions can be made? And I wonder whether, Eric, it might be an opportunity for you to talk a little bit about the new major that you have in ESS that combines policy and science as well.
Yeah, that's a good point, Jim. So I think the field of science is been evolving quite a bit to go outside the realm of the academia, the pure academia of natural science, to reach out to people who are actually working on adaptation and mitigation strategies. So engineers and social scientists, so that we can connect the natural science more with the public, policymakers, stakeholders, because that's really important to do. I think the scope of what we do in science is to understand how the system works and be able to make projection of what the future might look like. But we don't want in a position where we have to wait until that future to say, I told you so. We want to prevent some of these scenarios of futuristic scenarios that are not good for public health and are not good for flooding of coastal areas, that are not good for biodiversity, and not good for wildfires. So working to have a better chain of communication between natural sciences, engineering solutions, and communicating that to stakeholders is probably at the crux of what we're doing right now at UCI and across the country, so that we have this sort of a team effort on that to bring solutions to the problem. We know the causes, we know the impacts it may have on all of us, but there are also solutions, practical solutions. So Jim was mentioning decarbonizing our economy is the top priority, and I absolutely agree with that. From the standpoint of ice sheets, I even go beyond that. I said, yes, we need to decarbonize our economy, but we also went a little bit too far in spewing CO2 in the atmosphere. It's not a sustainable environment down the line for ice sheets in Greenland and Antarctica. Even if we stabilize the climate to 1.5 degree above pre-industrial, or worse, a 2 degree, we're going to keep melting these ice sheets at accelerating rate over the coming century. And this is not something most of us are probably ready to accept. If we say, you know, sea level is going to rise in the coast of California, possibly 1 meter, maybe 2 meters, maybe more, I'm sure a lot of people along the coastline will not be very happy about that if they know it's going to affect a little bit themselves, certainly their children and grandchildren. But there are solutions to that, but the solutions need sort of a massive effort across a society. If we do a big effort at UCI, that's great, even in California, but we understand that this is an effort that needs to take place at the scale of the entire world to decarbonize the economy, to bring clean energy. And I also think we need to find some ways to clean up the milk that's spilled on the ground. Eventually, that will be an important area of activity. We'll have to develop some economically viable technologies for that. The technology for decarbonizing our economy exists already, but to sequester carbon from the atmosphere back in the ground is a little bit more challenging if you want to do it in a scalable fashion, in an economic way. So we're working on that, but none of us scientists were necessarily trained to be great communicators and to have a natural potency to work with engineers and social scientists and reach out to public and policymakers to work together. We were not educated to operate in that way. So we're transforming that, but we are pushed by students. The student body, a lot of the young people who understand the risk of climate change, they want to work on solutions more than anything. So they embrace this concept that we as scientists are trying to connect more with engineers and social scientists and the public and stakeholders. And I think we've made some great strides in that, and we plan to do a lot more in the coming years. It's really, really important.
Yeah, let me echo a couple things, and I'll try to address some of the questions too that are popping up a little bit. You know, I think Eric said this robustly, but I mean, one of the goals is we'd like to collaborate with folks across campus and really around the world. For example, one of the things that there are folks in the Earth Systems Science Department doing, trying to figure out, look, if you have a limited amount of time and resources and energy, what are the specific things that we as a society should be doing that would move the needle the most? There's lots of things you can do that will decrease the carbon footprint, but what are the things that are really going to matter? What are the really hard problems? So for example, long haul shipping is a hard thing to do. So one of the questions in the chat was, what's the benefit, CO2 benefits in electric cars versus say a hydrogen car, right? So electric cars are really good for short trips. That's because the batteries are heavy, but it's going to be hard to do a long haul shipping or even a big truck with an electric battery of the kind that we have now. But if you store the energy via hydrogen, you can do better that way. There was a question about thorium reactors. Let me just say this. We intend to have another one of these calls where we'll bring in domain experts, and we have on campus who are experts on nuclear energy and fusion and hydrogen, the hydrogen economy and building solar cells and this whole thing. This is part of a series, and we're going to have those conversations. You know, with that, can I ask any one of you? We don't have that many minutes left. I would like someone to brag about the new major that you have in ESS for undergraduates who are getting people who are interested in policy, but also giving them a background in the basic science. I don't know if you want to do that, Eric, or anybody else is welcome to do it.
I mean, I can take a stab at it.
Great. Okay. Thanks, Kathleen.
So yeah, I mean, this is something that we have been moving towards in our department since I arrived. We're fully aware that incorporating, you know, aspects of policy relevant science, training students who can go and work on policy or science communication is something that we wanted to do. And we also have had several faculty hires in the area of human systems, including one that we're currently searching for right now to help lead this program. But we have a new major. It's called Environmental Science and Policy. and it's joint with the Department of Urban Planning and Public Policy in the School of Social Ecology. And so it's growing quickly. I think we have over 230-ish majors, I think, right now. And we're just entering, I think this is just the second year that we've been fully operational with that major. And it really does provide, the goal is to provide students with the fundamental scientific background, understanding of the Earth system, understanding of climate change, and other global environmental changes. But they also take a series of courses in policy, in economics, other social science courses. And so those students we're just starting to see where they're going, but many of them are going to work for nonprofit organizations or into, we actually have a new section on our website that's highlighting a lot of the alumni and where they are. So that's probably a better place to look than what I can remember off the top of my head, but they're going to go on and do great things. A lot of them are going on to graduate school as well. And I think there's a lot of opportunities for PhD programs that are incorporating that sort of science and policy aspect, because it really is just so important right now.
If I can add something to Kathleen just briefly, I think this program is sort of educating the next generation climate change leaders. Right? It's basically people who have a detailed understanding of the natural science, the science of climate change, but they also have an appreciation of the impacts on humans and on policy. And I think this breadth of education for these students is absolutely critical for them to be proactive and efficient in being climate change leaders, which is what we need right now to operate this transformation, beneficial transformation to our society, right? I have to remind our audience, we're not going to tighten our belt. We're actually going to create a lot of jobs and very exciting jobs with plenty of opportunities for amazing discoveries and adventures.
So we're running out of time here. I want to give Jim the last word. I'm going to ask him something specific, motivated by Anusha's question. So it's a great question, a suggestion to have people go around and talk about solutions that they might implement to make things better. I think that topic is so big and so important. We're probably going to focus at least one entire conversation event around that. But I want to leave Jim with the last word. What do you think we should be doing as a society, both to sort of prepare ourselves, which probably for things that are almost certainly going to happen, but then also change our infrastructure in ways that will help things in the long run?
Let's see, I have kind of a specific and a more general response there to this. I think one is that, in California, there's a lot of excitement, I think, about diversifying the grid and connecting different energy sources to the grid. So supporting things where maybe we allow kind of the competition with different solar arrays or different natural energy sources to be able to provide energy to the grid, I think is really important. And maybe the monolithic utility structure is one that is good, but maybe we need to think broadly about integrating more competition and innovation for energy there. And I would say, like, from the work that I do, one of the things that I'm really excited about for a solution is I think we can do better on fires. I think we can detect them earlier. I think we can keep them out of ecosystems where they haven't really been prevalent before, like the Amazon forest that came up earlier, like the Arctic tundra. Fires are moving north into Arctic tundra. We want to keep them out of there because any smoke that's emitted might go up and deposit on Greenland, darkening that surface. You want to keep it very bright and keep the snow intact. So I think on fires, if we have early detection, we may actually need to suppress fires in ecosystems around the world where they haven't experienced fires. This will have great benefits for biodiversity, but we're moving into a world where fires are going to move into new systems and they're going to pull, this is kind of counterintuitive, but in the north, they'll actually pull the forests with them. Whereas in the tropics, you'll actually lose the forest. So I think, probably all of us have specific solutions, but I think that anything we can do to see scientific principles and the infrastructure and the resource that California is putting into cap and trade, if we can use that effectively to optimize the grid and get more natural energy sources on there, I think is for us locally and regionally a really important step towards decarbonizing, which is what we got to do to protect the ice sheets and keep us from creating a really large paleoclimate anomaly during the Anthropocene that matches a Paleo-Eocene thermal anomaly or the Cretaceous extinction event. We don't want to really go there.
Well, Jim, with that, I think this is a great time to end. A fairly uplifting, if not sobering, comment there to end it up. This is such an important topic. This will not be the last time we'll do it. Let me thank you again, Jim, Kathleen, and Eric for your time. Thanks to all of you who joined in and everyone who asked questions. If I didn't get to your questions, we're going to do this again on a very similar topic, and we'll have either a subset of this group or a whole new group of folks who can work to answer those questions. So thanks very much, and we'll see you next time. Bye-bye.
Thank you.
Thank you.